I'm Rosana Galindo, the founder and chief scientist of the consulting company Victrius Nexus Energy. And today I will be speaking about AI-driven TAN LCA for smarter CCUS. How can we think about unlocking intelligent decision-making and scalability? So starting with a quick quote. What if we could predict environmental and economic trade-offs before investing millions? So AI-driven TAN LCA might make it possible, is making it possible. So we, in carbon removal field in general, we are having many different stakeholders, not only the technology developer side, but also government, investors, private sector. So it's a massive common movement for everyone playing a really relevant role in this field together. But sometimes, actually many times, we as the practitioners of these methods and technologies, we see more than everyone that there is a lot of opportunities to align better all the expectations in between the sectors, in between the stakeholders. And let's take a look on this. So, well, for those here that are not much familiar and those that are not LCA or TAIA practitioners, I brought here a very summarized set of inputs and outputs for TAIA and LCA, and where we can implement artificial intelligence and machine learning, just to start our conversation. So here on the left side, we have TAIA, and a few cracking the problem, cracking the method, a very straightforward for stage. So first we start with the process engineering modeling. Then we go to the plant sizing and the cost calculation, doing calculations for CapEx, OpEx, or and also project finance with methods like discounted cash flow analysis, for example. And we go for a sort of sensitivity analysis or uncertainty analysis. So for each one of the stages, we have inputs and outputs. And the same way for lifecycle assessment, considering the four main stages, go and scope definition, venture analysis, impact assessment, and interpretation. So let's consider that for these both methods, those substages are they are complementary. And for all these stages, considering all inputs and outputs, there is a wealthy of opportunities to improve how we work with data collection and processing, predictive modeling, uncertainty analysis, optimization, the results and inputs, and also opportunities to implement real-time monitoring. So let's dig in a bit more detail with this. So, well, currently the literature about artificial intelligence, I put here machine learning because machine learning is an artificial intelligence method inside data science. So when we speak about artificial intelligence, there is a lot of sub practices and sub methods that we could consider. However, why it's more common to speak about machine learning inside TAIA and LCA? Because once those methods are, the goal is to understand variations in a given scenario, and also to is a decision-making tool. Machine learning is a method inside artificial intelligence that assists us more accurately on how to avoid uncertainty inside these decision makings. And this method inside data science is one of the most applying for the sort of problem. So that's why people that are start working with artificial intelligence for TAIA in LCA are focusing much more in machine learning. And this is what I brought for you today. And we have this paper from Martinez Ramon from 2024 that they bring for us four main trends of applications for TAIA machine learning. Sorry, TAIA and LCA. Actually, this paper is more for TAIA. For LCA, but we can also do a parallel analysis for tail, because the inputs and outputs might many times they work in parallel. So here you have data prediction for lifecycle inventories with a few benefits. So wide and fast predictions, and a few algorithmic examples we see here is deploying decision trees, DT, random forest codes, or autoencoders. Second, we have adaptive calculations for models involving rigorous and complex equations in process engineering simulations. So, for example, if we have inside Aspen Plus, let's say a more general, a common example of process engineering simulation. So, if we have a data set for a chemical compound that we are maybe getting some data from thermodynamics equations of states and parameters from literature. If there is some missing data there, we could also apply machine learning here to try to fill this gap and do a more accurate mass and energy balance estimation for this process engineering design. Third, you have data acquisition from descriptive variety data sets to generate LCI. So for lifecycle inventories, we could be very beneficial through correlation and manipulation of complex databases. So many times when you're defining the inventories, we have data from different sources, different databases. Many times they just can't talk with each other, let's say, in a more normalized way. And this is very, very relevant, the machine learning application in this case. A few algorithm examples, so I think I missed it, but we could also do a parallel analysis for data prediction, because when you're speaking about databases, decision trees, random forests, and autoencoders are also very beneficial techniques to be deployed for LCIs. Actually, this is one of the examples I brought to you later. I will be presenting you. And finally, you have also the optimization for impact assessment indicators. A few benefits: prediction of optimal environmental performances based on specific impact categories. So a few algorithms that can be put here: multi-objective genetic algorithms, artificial neural networks, and Boltzmann machine. Oops. Okay. Next, think a more broader perspective. So carbon removals in general, not only carbon capture and storage or carbon capture and utilization, but carbon removals in general, driven by AI and machine learning. So we need to think a few premises before starting implementing these methods inside our current 10 LCA. So for example, issues regarding scalability and deployment. So how specifically could we implement scalability, starting doing the scalability of given emerging methodology for technology, for example, by using data existing from other processes that are already commercialized at TRL levels or lower TRL levels. So how to do this cross-site analysis, optimization of low TRL processes, materials performance, and also for benchmarking. Thinking about monitoring operation. So here we have predictive maintenance, opportunities for predictive maintenance, systems control, energy efficiency monitoring, and process upgrading. So this side is all inside the facilities, or on the field in general, if we're speaking about transportation, for example. And governance. So performance in monitoring, prediction of population indicators, and automation of carbon credits. So if you think about the carbon markets and regulatory perspective, we could have a lot of opportunities also to deploy this driven AI machine learning methods. And more straightforward, saying about which opportunities we have for CCUS scaling in this case. So we could think about consultation of data sets, predictive modeling for emerging technologies, as already mentioned before, normalization of temporal spatial parameters, systems boundaries uniformization, co-product allocation and normalization, multi-criteria trade-offs aggregation, and long-term forecast scenarios. And here, opportunities for improving net zero technologies based on uncertainty. Here we have data collection and processes. So the integration of advanced artificial intelligence tools and also implement big data analysis. We can think about predictive modeling for uncertainty parameters and also time series forecast for future trends. The third pillar is uncertainty analysis. So including AI for Monte Carlo simulations of Bayesian inferences, for example, from the optimization perspective. So we could think about the implementation of stochastic and more robust techniques, a few scenario analysis for different future conditions, and real-time monitoring. And inside real-time monitoring, we have the pillar of adaptive management. And here we can start thinking about how we can translate this LCA and TEA for society in general by using AI, machine learning. So here we have the integration of Internet of Things, devices for data collection, straight from the society, adaptation of TEA and LCA models dynamically based on real-time data monitoring. And here about a few examples. So I'm not sure how we are with time, so I will jump a little bit faster on the sections because there are more examples, and we can discuss more about it in the Q&A section. So here, speaking specifically about TEA, a few opportunities that we have is for CapEx calculations. So for example, chasing data for equipment costs, labor installation, piping, instrumentation and control, foundations and support. And for OpEx, we have opportunities for chasing data on maintenance and labor costs, feedstocks, raw materials, utilities, electricity, consumables, and waste disposal. So for example, if you are doing those assessments for in academia, we can find data from existing literature reports, but when you are speaking about doing these assessments for real customers, for let's say real life applications with clients, with companies, startups, and so on. Well, one thing that is very challenging at all at industry sector, not only in industry, but specifically speaking about industries, ensure that each department inside the company tracks data. And honestly, they typically don't track, especially if you're speaking about emerging technologies where companies are small, they are still growing like startups. Many times, like 2-3 people do everything inside the company. They just don't have data. And how could we ensure this company will be scaling in a sustainable way their operations if they are not tracking data and we don't have how to monitor and to predict this scalability? So with AI machine learning, we could have an option to assist these companies, for example. And here, very quickly, I brought an example for a machine learning application using random forest imputation, RFI. So for example, here we can think about data collection, adjusting of missing data, missing or noisy data inside the data sets. And how it works by predicting missing database and correlated data. And here we have as a first stage, the pre-processing of no variables. So for example, we have the data set and then different data sets, and then we need to think about how to normalize all those different sources of inputs. And we also have the encoded categorical correlation. So after normalizing the data, we go to the encoding session. And this encoding goes straight to the random forest imputation algorithm. What takes in consideration what enables handle of mixed data, linear and non-linear interaction between variables, what's really important, because many databases, if we transform the database in mathematical equations, to understand how is the uncertainty of those data for a given data set. For example, if you convert many matrices, a matrice. So many times, if we convert different data sets from different sources into matrices, there is a high risk of the vectors generated from this matrix they don't speak with each other because they're not normalized. So this is what the RFI, the random forest imputation, does by linearizing non-linear input variables. And you also have here the multicollinearity and detection of noisy values. So how to detect those let's say, for example, if you have a data set with a lot of same data in different places. So this should be an example of noisy data, for example. And here is the steps for these data sets, how they work. So I have first data set, let's say, that's not refined. An example, we have mass and energy balances, the plant size and costs. Then we implement these RFI algorithms that analyze, normalize, and validate data set A by transforming matrices into vectors and identify the correlations between the patterns. And a typical tool that we use for this sort of algorithms, there is a variety of different tools you can use to model these algorithms, but people typically do in Python, and I particularly prefer Python because it's free. And since we're speaking here about how to make models available on open source, it's more, I think it's more reliable and it's more accessible. And one package that is indicated to using Python for this sort of modeling is scikit-learn. After doing the RF algorithm, we have a new data set is linearized and normalized and also validated according to the predicted algorithm. Here is an example for the LCA application. So I brought the example for autoencoder algorithm. So for example, we can apply when trying to estimate missing data across complex data sets. So for example, to estimate lifecycle inventories or the impact assessments. And how it works through data collection, analysis, and validation across variety data sets through encoders and decoders, high to low dimension. So we might ask, what's the difference between random forests and autoencoders? Actually, both are methods for refining data from databases, but they work in a different way. So here we work with matrix, expanded and compressed and expanded. And in the first example, they just linearize. Here we are speaking about linear and non-linear, but in different dimensions. We're speaking about matricial systems, more for the mathematical modeling. So here are a few examples. I brought a few impact categories that we can that might be useful, and they are key for CCUS applications like GHG emissions, energy use, water use, land occupation, toxicity categories. And very summarized. So how does the autoencoder algorithm work? So same way, we have an LCI inventory with missing data, with noisy data. So for example, we have data from foreground, background, different data sets for mass and energy balances and so on. And our goal is to normalize everything. So here we deploy the autoencoder algorithm that will first compress, bring all those different data sets together, transform each one of them in matrix systems, compress those matrices to bring from a high to a low dimension data set. Then we apply a training inside the model that will do the correlations and linearize the vector, because let's say the data sets might be in 10 dimensions, 5 dimensions, 8 dimensions. The idea is here to bring to very base dimensions like 2 or 1, considering that the one dimension is a vector. And after linearizing and normalizing, adjusting everything in one dimension, the algorithm expands again these data sets and crack in different data sets. So this is the decoding stage. And typical tools that we use to this step is TensorFlow, PyTorch, also a package for Python. And as a result, we have the entire LCA dataset refined with a refined version. And here about a few general applications and resources. So examples for applications: inputs for data collection. We can think about mass and energy balances to predict chemical prices, price for equipments, electricity costs through our database, for example, government database. And how can we apply? So artificial intelligence using large language models, for example, to chase data properly in literature review. A second option should be data estimates for consumption prices. So that was more similar to the example I brought for random forests in autoencoders, applying machine learning. So those techniques are also classified under clustering, regression, and time series optimization. And also data analysis. So for data analysis, you can think about extraction, aggregation, and visualization for outputs mainly. Here we can think about workflow management, regressions, model, and visualization. And a few outputs. We could also apply those techniques into sensitivity analysis to refine equipments and flows, costs for example, CAPEX and OPEX, using machine learning, again, regression analysis, clustering, time series optimization, also for prediction analysis to understand benchmarking of new technologies and markets, future scenarios through large language models or time series regression analysis. And finally, we can also think about the same way for the inputs, the data analysis applying direct methods like extraction and aggregation and visualization methods. And here to finalize our section, because I think we are also out of time. So best practice to deploy AI-driven methods to LCA and TEA. So a few stages that I brought here that should be interesting for us to discuss after this talk is thinking about the clarity on AI machine learning users. So in other words, the purpose. So first, do we really need to apply an advanced method for a complex algorithm? So how this application will benefit our existing assessment? Because many times we just don't need, right? Like we have been doing 10 LCA during years, all of us, without those advanced methods. And okay, it works, but why? So would this reduce costs inside my department? Would this speed up time of our researches? Would this bring more, reduce the uncertainty in the analysis? Would this bring more normalized data sets? So what's the benefit, the real benefit of deploying? So I think that here is not just because the methods are cool, because it's hyping, blah, 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 but it's more because is it really needed? Because building these algorithms also takes time. So I think bringing clarity is also fundamental here to start this sort of modeling. Providing standards. So standards are fundamental for LCA. We already have a few we're refining for TEA. We are start thinking about, but as we advance in this conversation, so I think it's fundamental we also think about how to include AI methods inside these standards. So it's fundamental to ensure that everything are well aligned, the goals are aligned, because if it's not well monitored, this deployment, it can easily generate a lack of transparency in the models. And how to prevent this? To ensure data quality in processing, validation of those methods. So how can we ensure that those methods are not only validated inside our department, inside our research institution, but also it's easy to validate to our peers if you're submitting in for a journal, the publication, or if we are submitting, assisting our clients to submit for a certification through a certification process for carbon markets, for example. How to ensure the reviewers will also be able to validate those methods to ensure the transparency in the model. So again, it's a chain. You know, we need all those very well aligned stages to ensure transparency for all models in all stages of the process. And finally, reproducibility. So how to communicate? Because, for example, if you are speaking about academia, it's easier to make the publications, the data used on publications available. But many times for private sector, for companies and certification for organizations for certification and regulatory frameworks, it's not possible. So how to ensure we have this transparency in the models, but also that others can reproduce in a reliable way those methods. And that's it. So thank you very much for your time today.